Hello, I'm Kelsey Cairns, and it is my privilege to present a demonstration today investigating secure delivery of PMU data in the smart grid. This is a combined effort by Yujie Wang, Qingwei Cheng, and our advisor, Carl Hauser. Our demonstration today will focus on data injection attacks against PMU data streams. To set the stage for this demonstration, consider the continental scale deployment of PMUs installed over the last few years and depicted here. PMU data will be used increasingly in both centralized and distributed applications. It is likely that data from any one PMU will be used by multiple applications. This motivates the need for some sort of multicast or publish-subscribe data delivery, even though today's PMUs are typically only configured for point-to-point communication using either TCP or UDP transport protocols. You may be familiar with papers published beginning in 2009 that assess the effects of false data injection on state estimation algorithms. These papers consider the effects of bad data at the level of the algorithms themselves, without considering the practicality of injecting data either through the meters or the communication channels. False data injection would be even more of a problem for applications such as special protection schemes that have no intrinsic protection against bad data. It is our opinion that data authentication should be available for all streams to critical applications, given the practical attacks that we are about to demonstrate. To set the stage for our attacks, we have set up a PMU in our lab at WSU, which is sending 3 identical streams of measurements to display applications here in this lab at UIUC. One of the streams is delivered using TCP. The other 2 streams are delivered using UDP. The UDP streams are delivered using the GridStat data dissemination middleware. GridStat allows us to quickly and easily configure both authentication and encryption for different streams. One of our GridStat streams is unprotected, and the other GridStat stream is protected using TCIPG's TVOTS authentication. Note that since GridStat capabilities are not yet implemented for commercial endpoint devices, that the GridStat functionality for this demonstration is added with separate nodes that are shown in the figure. Looking at the screens, we have across the top our 3 streams of measurements. On the left side, we have our stream that is delivered using TCP. In the center, we have our unprotected UDP stream, and here we have our stream protected by our TVOTS implementation running over UDP. On the left side, we have our attack console, which we will use to launch attacks against each of the 3 streams in turn. And at the bottom, we have TVOTS output, which will indicate when a signature is rejected. For our first demonstration, we'll look at data injected into the TCP stream. TCP is widely used in the internet for browsing the web, sending and receiving email, and any other application where in-order reliable delivery of messages is required. TCP is also widely studied for attacks such as data injection and hijacking. A successful attack requires knowing the addresses of the endpoints, but also an ever-changing sequence number, which increments by 1 for each byte sent. Knowing the endpoint addresses is typically not too hard in the internet. However, knowing the sequence number is quite a bit more difficult, since connections are very often short-lived and the data is also sent sporadically. At the moment, you can see that the data from the TCP stream, now also shown here, matches the other 2 streams. As we start our attack from our lab at WSU, you can see that the data is now jumping to an injected value. The vulnerability we are exploiting is that in the PMU context, connections live for days, weeks, maybe even months. An attacker that figures out the sequence number at any single point in time can use this knowledge over an extended period of time to inject data using the pace tracking attack that we have going here. Going on to our next demonstration, we will look at data injected into the UDP stream. As we start our attack against UDP, we see that data is now sporadic, depending on which message, the injected message or the real message arrives first. Note that in the TCP attack, the real message was suppressed in favor of the injected data. However, in this application, or in this context, both the correct data and the injected data are delivered to the application. An application could, if so designed, detect that it was being attacked, but it would have no way to tell which of the messages it was seeing was the correct data. As we've described in previous years, achieving low latency delivery of messages for multicast environments is quite challenging. Schemes based on public keys, such as RSA or DSA, have quite a high computational overhead and add significant latency to message delivery. Delayed key release schemes do not have the same computational overhead, but on a wide deployment such as this one, messages received would require several millisecond delay before they could be authenticated. Symmetric key schemes, and this is the approach taken by the 61850-90-5 protocol, or standard, also have a low computational overhead, but these schemes are vulnerable to defection by any of the recipients. TVOTS is a scheme that is low latency and secure for multicast. As we start our attack against our TVOTS stream, you see that the GridStat output window is telling us that messages are being rejected. The data display shows that the messages that are receiving contain the correct value, since it is the same as the other streams. In conclusion, false data injection is a serious problem. Both TCP and UDP are vulnerable, and today's PMUs are typically not configured with any type of data authentication. VPNs are used to protect traffic between substations and control centers, but it is our opinion that message authentication is both desirable and feasible to protect against attacks launched from within either substations or control centers. TVOTS provides low latency data authentication that is safe for multicast environments. The only other schemes that achieve these latencies are schemes based on symmetric keys, and these, again, are either vulnerable to defection by receivers or require separate signature for each receiver. TVOTS was designed with this problem in mind, and we are quite proud to say that TVOTS, which started as a TCIP project, has now reached maturity in TCIPG work and is now up and running as an implemented protocol in our GridStat framework.